Hello everyone and welcome to the presentation of our paper titled Decentralized Self-Adaptive Systems, a Mapping Study. Maybe a quick introduction first. My name is Federico Quin. I'm currently a PhD student at Decentralized KU Leuven under the supervision of Weyns. I've done this work together with Weyns and also together with Omid Gheibi. First things first, I'll give a quick overview of what I'm going to be talking about in this presentation. I'm first going to go through an introduction where I explain what we are trying to accomplish with this mapping study and what the scope of the study was, as well as some high-level results of it. Next, I'll go through each research question listed out in the introduction and go through the results of those. After that, using the data that we have gathered from answering the research questions, I'll propose two enhanced architectural patterns, which will become a bit more clear later on in the presentation. And then lastly, I'll conclude with a few concluding remarks and also the direction we want to work toward in the future. Looking a bit further in terms of the scope of the study, we mainly focus on architecture-based adaptation, and more specifically, we are looking at MAPE-based architectures. Reflecting back on those basic adaptation functions mentioned in the previous slide, when we are talking about basic adaptation functions, we are referencing specifically one of these MAPE functions, and in more detail, one of the monitoring, analyzing, planning, or executing functions. We call all of these basic adaptation functions. This gives an outline of the first scope of the study. Besides this, we also scope the mapping study based on the degree of decentralization that is employed. We are specifically interested in studies that apply some form of decentralization with some minimum requirement. The minimum requirement that we list is that at least one of the basic adaptation functions is organized in a decentralized fashion, meaning that they map to multiple components, and not just one, and that these multiple components interact with each other in terms of coordination and communication. We apply this as an additional criteria for a study to be included. And then lastly, we are specifically focusing on 20 main venues, including SEAMS, SASO, TAS, which mainly focus on self-adaptation and work closely related to self-adaptation. We have performed an automatic search query over multiple online libraries and applied these criteria to retrieve these results. Besides the automatic search query, we also applied snowballing to a community study on decentralized adaptation published in 2013, where the authors present 5 different types of patterns to organize and describe decentralized self-adaptive systems. We look at papers that have cited this community study from 2013, apply the same kind of inclusion criteria as just mentioned, and finally include these studies that are deemed relevant based on the criteria just listed. As a result of this, we have collected 96 primary studies, 48 of them resulting from the search query, and the other remaining 48 of them resulting from the snowballing process. In terms of the most popular venue that we have observed, it was SEAMS with 13 primary studies. And then in terms of publication year, we can see that starting from 2008 or even 2010, that there is a steady increase in the interest of decentralization in the context of self-adaptation, which is a nice thing to see, seeing that it is still a very relevant topic in the research community today. Moving on to the first research question related to motivation, we attempt to find an answer to the following questions. So first, why do people choose for a decentralized solution? And second, what are the benefits or the implications of choosing for a decentralized solution? When looking at the results, in terms of motivation, the most prevalent motivations are nature of the problem and scalability. With nature of the problem, we mean specifically that the use case where the authors apply self-adaptation or decentralized self-adaptation kind of has an inherent problem that necessitates decentralization. So for example, if you have a system composed of multiple subsystems where no central authority is allowed to exist or should exist, then of course the problem dictates the need for a decentralized solution. Other than that, we have scalability also, which is no big surprise. If you want to scale up to bigger systems and you want some sort of self-adaptive solution in there, a centralized feedback loop might not do the trick anymore. And in that sense, a decentralized solution can cover this basis more accurately. Similarly, for reliability, to make a system more reliable, the removal of a single point of failure is paramount. In that sense, a decentralized solution can take care of that part as well. Then, in terms of trade-offs, we have 2 trade-offs that we want to highlight. The first one relates to design complexity. This trade-off is maybe a bit counterintuitive. Personally, I think I can speak for most people as well. I think of design complexity as a negative in a decentralized context, since designing decentralized systems and managing decentralization concepts within these systems makes things a lot more complicated. Surprisingly, however, some authors listed design complexity as a positive, since the self-adaptation mechanism that they had to design for those smaller subsystems was easier to design itself. Other than that, another listed trade-off, which is often mentioned, is suboptimal solutions, which is kind of an implication of applying decentralization. This is potentially not always necessarily true, but in most cases decentralization introduces some overhead in the system, which entails a form of inefficiency in the solution. Or, on the other hand, no overhead might imply incomplete information about the system, resulting in additional complexity to choose a system-wide optimal solution. Moving on to research question 2, we are specifically interested in terms of architecture. Thinking back on the single adaptation functions mentioned earlier, we are first trying to look at what basic adaptation functions are mostly used for decentralization. In other words, which individual map functions are mostly decentralized. Besides this, we are also look at the aggregated decentralized map functions. So what we mean by this is, on a case-by-case basis, we look at combinations of different adaptation functions and see which combinations are being decentralized together in these individual cases. Additionally, we also want to map the architectures used to realize decentralized self-adaptation in the primary studies to the patterns identified in the community paper earlier. To the right here, we show a few of these patterns. We thus want to identify these patterns in the primary studies that we have gathered, and if none of the patterns from the community paper match directly, we want to identify potentially new patterns that might not have been covered in the community paper, or identify new compound patterns, which I will come back to in a little bit. As a quick example of one of the community paper patterns, information sharing is a pattern where the monitoring component of the map loop can interact with different monitoring components of other map loops. In this way, they can share information to organize coordination between the different parts of the system and to facilitate adaptation in a decentralized context. Going through with single decentralized adaptation functions, we can see here that the monitoring function is the most popular one of all of them with 62 instances. Overall, however, we can still see that most of the different adaptation functions are decentralized and are quite well distributed in terms of decentralization frequency. If we look at jointly decentralized adaptation functions, or in other words, the aggregated decentralized map functions we were talking about earlier, we see that monitor executor is quite often combined. This observation plays quite well into one of the patterns outlined in the community paper. One of the patterns listed in the community paper is a master-slave architecture, where the monitoring and executor functions are organized in a decentralized fashion, and where analysis and planning are organized in a more centralized way. In that sense, this observation maps quite well to this pattern. It is thus not that surprising that this combination is quite often used. Other than that, the complete map loop is also often decentralized, meaning we have multiple map loops within the system that coordinate with each other in all kinds of ways. Now, looking further in terms of interaction patterns being used, we have for one hierarchical control, which is very often used when we have multiple adaptation layers, so to speak, having multiple feedback loops on top of each other. And the idea here is that these different feedback loops operate on a different level or different layers in this hierarchy. They reason and work on different levels of abstraction, concerning themselves with different goals, and each of them trying to manage the system in their respective way. Other than that, we have information sharing that is also often used, which is for example, the first example that I quickly described earlier, where we exchange monitor data between other monitors and then try to orchestrate self-adaptation using this additional context or information. Now, besides these 5 patterns from the community paper, we have identified some compound patterns. A compound pattern, in this context, is a pattern that consists of a combination of the existing patterns that we have available already. So more concretely, out of the 5 patterns that we have, the case might not directly map to just one of those patterns. Rather, they make use of the combination of two of these patterns. In essence, it combines one pattern on top of another pattern that generally functions on a different level of abstraction or concerns. Next, moving over to research question 3 about coordination and communication. First, we are interested in what type of communication is used to enable coordination. Examples include things such as sending simple messages or broadcasting messages between components. And then second, we look at what kind of coordination mechanisms are used to provide a decentralized self-adaptation solution. In other words, what kind of coordination schemes are being used, what kind of protocols can we find. An example here is coordination orchestrated via a client-server model. Looking at results, we can see that for type of communication, we have intermediary messaging system mostly being used. With intermediary messaging system, we are referencing, for example, some sort of middleware, which provides some message passing interfaces or even defines some distributed queues. Other than that, direct messaging is also quite popular in the sense that you have, for example, two different components that directly exchange some messages between each other. In terms of types of coordination, we have client-server as the most used one. This mechanism is generally quite broadly used and also fits the master-slave architecture quite well. Other than that, we have process-based coordination as well, which is quite often used. What we mean by process-based is that there are clearly defined interfaces between producers and consumers with clear interactions between them. So more concretely, the paper provides an outline or some sort of protocol where there is a clear interaction and order between producers and consumers, which might represent two different types of components in the system. Lastly, we take a look at limitations and challenges in the last research question. We will list a few that are most often cited. The first limitation is modeling restrictions. An example of a modeling restriction is the extent to which uncertainties can be modeled. Next, underlying assumptions, where, for example, an assumption is being made about a communication channel. Assumptions here include perfect communication channels with no messages lost or overhead. Another limitation listed is overhead and inefficiencies due to, for example, the amount of messages that are being sent, introducing a lot of overhead in the system. In terms of open challenges that still remain, we have enhanced coordination mechanisms and improved decision-making process. Both of these are kind of part of the same vein, where parts of the system, such as the coordination mechanism or the decision-making process, are improved by, for example, enhancing internal mechanisms, providing advanced reasoning capabilities, etc. Next, we have improving overall system goals, where we are thinking about resolving some suboptimality of the solution, similar to what was listed as a trade-off in the first research question. Lastly, we have providing guarantees, for example, providing some formal or even informal analysis of the solutions to provide something more to the reader. Now, in what direction do we want to move forward with this? We present some enhanced patterns here, starting, for example, with the information sharing pattern. The question is, how would we enhance this pattern? What we propose is to include a coordination model and a coordination channel to the pattern itself to model these aspects explicitly as well. So what does this concretely mean? The coordination model represents the coordination mechanisms that we have used to facilitate coordination, and the coordination channel represents the type of communication that is used to enable this coordination model. An example of what this could look like for information sharing is the following. So using a tuple-based coordination with an intermediate messaging system. In information sharing, the monitor monitors some information, processes this information into a tuple, puts this tuple in the tuple space. Putting this tuple in the tuple space might be done with an intermediate messaging system, such as a middleware which maintains and manages those tuples. And then the other monitors can fetch these tuples, in other words, fetch information from another monitor, and try to make adaptation decisions with this information in mind. This is an example of an enhanced pattern where we explicitly model the coordination and the communication in the system as well. Similarly, we can also enhance the regional planning pattern, in which we have different regions, which are all controlled by one central planner within each region. And we can enhance this pattern by, for example, providing a market mechanism as a coordination model and a direct messaging system as the coordination channel. In more detail, planners make bids and generate offers with regard to possible adaptation options or adaptation plans that are in their best interest. And the central idea is that they use the market to advocate for their own interests and goals, trade plans, and ultimately decide on an adaptation plan in the end. They can do this by directly exchanging messages in between them in terms of providing those bids and offers, as well as providing adaptation plans to other planners. Finally, I want to conclude with some last closing remarks. The first remark being that there is a steady increasing interest in decentralized self-adaptive systems, which is a great thing to see. Next, we have noticed that the architectural patterns identified in the community paper from before cover the collected decentralized solutions quite well. Most of the use cases that we have seen map directly to one of the patterns identified in the paper, or in most other use cases, even a compound pattern constructed out of 2 of the original 5 patterns in the paper maps the architecture quite well. What we have also seen is that there is a very broad use of different coordination mechanisms and communication types, meaning that there is definitely not a one-size-fits-all solution. In terms of future planning opportunity and direction, We want to identify further relationships between different communication types, coordination mechanisms, and architectural patterns, and see if we can find any links or relations between these three to provide more advanced patterns and ultimately a more constructive way of designing those decentralized self-adaptive systems. In an even further next step, we would like to reify these enhanced patterns from before into a framework to provide a more structured solution to design decentralized self-adaptive systems. Thank you for listening to my presentation about our paper. If you have any questions, I will be more than happy to answer them.